We like to thank introduce the organizer, Dr. Sekisaka. He comes from Meiji University. Today, his topic is topological approach to the stability problem of traveling waves. Let's welcome his talk.
Okay, so thank you for your kind introduction and opportunity to give this talk. It's a long time not know she, and so nice to meet you all.
Yeah.
So I'm Ayuki Sekisaka from Meiji University in Japan. So I have been studying existence and stability problems of solutions of partial differential equations such as reaction diffusion systems using topological and dynamical theory method. So in this talk, I will give an overview of topological method constructed with particular focus on the stability problems or briefly introduce some applications. Okay. Oh, can you share slide?
Yes.
Okay. So consider the stability problem of traveling waves in reaction diffusion systems. So RDS is the, so this method can be applied to more than just reaction diffusion systems, as you will see in some application that will. So we consider the reaction diffusion equations, and so we take a moving frame or moving coordinate x equal x minus ct. So c is the speed of traveling waves. So for Cauchy and the time t coordinate, so equation 1 written as the this equation 2. And so traveling waves are stationary solution of equation 2. That is so a traveling wave satisfies this equation, so equation 3. And so equation 3 is written as the first order ordinary differential equations, or so-called vector field or R2 n dimensional Euclidean space. Such rewriting into the vector field is very useful when applying dynamical theory and geometrical theory to existence and stability problems. Okay, so this is just rewriting to the equation. So each equation has a corresponding solution. So for example, traveling waves for equation 1, so partial differential equations. So constant solutions correspond to the equilibrium point of the vector field. And so traveling front from a constant solution U1 to U2 corresponds to the heteroclinic orbit from U1 to U2 for the vector field. And so traveling pulses with respect to constant solution U0 correspond to the homoclinic orbit from a small U0 in the vector field as equation 4. So suppose we have traveling waves for equation 1. So we have traveling waves. So next we consider the spectral stability of the traveling waves. So like this. So equation 4. So then we consider the linearized equation around the traveling waves. So like this. So equation 4 is a linearized equation around the traveling waves. So then spectral problem of traveling wave is given by the linearized operator defined by the right-hand side of equation 4. So like this, equation 5 is a spectral problem of traveling waves. So in this talk, we consider this linearized operator L on the Banach space, bounded and uniformly continuous functions or usual L2 space. So we consider such space. So, okay, so the spectral problem, so equation 5 is equivalent to the first order ordinary differential equations. So like this, so equation 6 is a spectral problem equivalent to spectral problem. So this is also first order ordinary differential equation, so vector field on the space is a 2n dimensional complex vector space C2n. So simply we express as so final equation. Okay, so we to show that the traveling wave is spectrally stable, so we need to show the following two conditions. So first, so 0 is a simple eigenvalue of L. So 0 is always the eigenvalues of L generated by the parallel symmetry of traveling waves. And so eigenfunction is a derivative of traveling waves. And so second, so all non-zero spectra are contained in the left half plane in the complex space, a complex plane C. So or like this. So there is a positive beta, and so C beta is defined by so like this.
But is this the left half plane or right half plane? Sorry.
Sorry. So
It's smaller, maybe smaller than minus beta, right? Or
sorry. So I mistake. So smaller. So left.
Sure, sure.
Oh, sorry.
No problem. Yes, thank you.
Yes, yes.
So
But we automatically see is least than beta.
So, okay, thank you. So, and so my interest is to use a topological approach to extract information about the distribution of spectra. So, in particular, so distribution of eigenvalues. So, exist or so non-exist in the so right half plane or so left half plane. Okay, so usually so the traveling wave is considered to converge to the stationary constant solutions at so infinity. So therefore also like this. So traveling waves converge to the constant solution u plus and u minus tend to Cauchy to plus infinity and minus infinity. So then so therefore so the matrix of linear systems converges to the constant matrix A plus minus lambda with respect to the linearized equation around the constant solution u plus and u minus, so correspond to the plus and plus minus. Okay, so we assume that the matrices of infinity, so A plus and A minus, are called as the asymptotic matrices. So we assume that matrices satisfy the following properties. So following properties. So A plus and A minus is a hyperbolic matrix. And so dimension of unstable and subspaces are equal. So for all lambda in C beta, so this is so it is a mistake. So okay. So this is not a mistake. So we consider that right half plane because we want to show the stability of traveling waves. So stability or instability shows that lambda exists in C beta or C. So if okay, sorry. So we interested in the stability problem of traveling waves in C beta. So in particular, so beta is 0. So right half plane. If the eigenvalue exists in right half plane, so traveling waves is instability, is unstable. So we consider such a domain C beta. So we assume that for all lambda in C beta, so a plus minus lambda is a hyperbolic, and so unstable dimension, dimension of unstable subspace are equals. Okay, so phi z xi lambda is the fundamental solution matrix for the linear systems. Also, this is called as evolution operator for linear systems. So define the unstable and stable subspaces for such linear systems like this. So EU xi lambda and ES xi lambda equals like this and like this. So these subspaces are set of solutions. So unstable subspace consists of solution of decay at xi, also zeta tend to minus infinity, and so stable means that this set consists of all solution of decay at zeta to plus infinity. So okay, so fundamental solution matrix phi is in the linearized general linear group, as it is means that determinant of phi not is not equal to 0. So it is there exists as inverse of phi. So it acts transitively to any k-dimensional subspace in to n-dimensional vector space. So it means that k-dimensional subspaces maps to the k-dimensional subspace for phi because it is in generalized linear group. So this relation means that linear system on a 2n-dimensional vector space induces the vector field on the Grassmannian manifold of k-dimensional subspaces expressed as gk C2n. So induces vector field expressed as equation 7 like this. So it is induced by the linear system y dash equal a z xi lambda y. Okay. Okay, so the Grassmannian manifold GKC2N is defined by the set of all K plane in 2n dimensional complex vector space. So like this. So first equation. It is also defined as the homogeneous space. So second equation like this. The important factor is that all K-plane are represented as points in the Grassmannian GK2N. So like this. So if V subset a K-dimensional subspace in the 2n-dimensional complex space, then so a corresponding point in GK C2N. So we denote this correspondence by these symbols or these symbols. So square or sorry, so this symbol. This fact is well known that so lambda is an eigenvalue of L if and only if so unstable subspace and stable subspaces EU and ES intersect a non-triviality. So lambda is an eigenvalue in this setting. So if and only if this intersection exists, so non-zero vector. Okay, so we consider this intersection problem in the Grassmann manifold in so GK to C2N. Okay, so each n-dimensional subspace corresponds to the point in the Grassmannian. So therefore, so there exists a map. So I equals to minus infinity to infinity. So it is a compactification of R. So it is a closed interval. And so omega subset C, it is, this is a simply connected bounded domain. We can take, so Xi is in I, and so lambda is in omega. So there is exists a map, so Xi and lambda maps to so unstable subspaces, and so is in the Grassmannian manifold. It is a point of the Grassmannian manifold. And so we remark that so unstable and stable subspaces satisfies the following properties in the Grassmannian manifold. So like this, so Xi to minus infinity, so EU Xi to so EU minus lambda. So EU minus lambda is a unstable subspaces of a constant matrix A minus lambda. And so ES Xi lambda to converges to this ES plus lambda. So ES plus lambda is a stable subspaces with respect to the constant matrix A plus lambda. Oh, sorry. Here. Yeah, so stable and unstable subspaces with respect to the A plus minus lambda. Okay. Also, since we consider the space variable Xi is in the closed interval minus infinity to infinity, and so lambda is in omega. Omega is homeomorphic to two-dimensional disk. So we can obtain a vector field on the two-dimensional sphere, so two sphere, as follows. So two sphere constructed by so like this. So boundary of I times omega, and so I times boundary of omega. So it is so topological two-dimensional sphere. This map from so two-dimensional sphere to Grassmannian over n-dimensional subspaces. So from this relation, we can obtain a vector bundle on the two-dimensional sphere, two sphere. It is called a pullback bundle of tautological bundle of Grassmannian manifold. So like this. So this is so we can obtain the pullback bundle. So tautological bundle means that so right side arrows like this. And so, okay, so it is well known that the homotopy type of a vector bundle of on two sphere is determined by the map from two sphere to Grassmannian. And so next theorem is so very important result, both topologically and analytically. So Alexander, Gardner, and so Jones showed that so let script E is a pullback bundle such constructed bundle, and C1 script E is a first Chan number of such constructed vector bundle. So the first Chan number is characterizes the homotopy type of a complex vector bundle, and so it is give as a positive integer in this case. So Alexander Gardner Jones showed that so first Chan number of such pullback bundle coincides with the number of eigenvalues in omega with their multiplicity. So, so in this case, so we consider the two-dimensional sphere contains so omega. We remark that. So Alexander Gardner Jones shows that so this relation, and so the first Chan number is called as a stability index. So because so this topological invariant arranging stability problem of traveling waves, so as called stability index. Okay, so similar result is so also well known. So we can define the analytical analytical function as follows. So d lambda equals so determinant of so y1 to yn and yn plus 1 to y2n. So column of so each column is such solutions. So y1 to yn is in so unstable subspaces. So we can take so these solutions independent solutions in EU. And so yn plus 1 to y2n is in stable subspaces. And so these solutions are independent in ES. So each solutions are independent solutions of each subspace. We can take such solutions. And so we and define the Evans function, d lambda is defined by the determinant of these solutions. So so Evans first and originally showed so 1972 the eigenvalue of L coincide with the zero of Evans function. And so using winding number of analytic function, so we have the similar result of stability index. So like this, so the winding number of Evans function of boundary omega is equal to the number of eigenvalues in omega. Okay, so the Alexander Gardner Jones theory gives a relation between the analytic Evans function for finding exponentially decaying solutions at infinity and the first Chan number of a complex vector bundle created from an eigenvalue problem. So topologically important is the fact that the information of eigenvalues can be obtained as the homotopy type of a vector bundle or so such maps, not as a first Chan number. So for example, in homology group theory, so stability index is given by such induces homomorphism maps. So two-dimensional homology group of a two-dimensional sphere to a two-dimensional homologic group of a Grassmannian. So 10 to 1 to n. N is so positive integer. It is equal to the first Chan number. And so in homotopy group theory, so it is shown by Ni 1997. So stability index is in the two-dimensional homotopy groups in the Grassmannian Gn C2n. So these are also called stability indexes. So because of these homotopy type are equal. Okay, so based on these theories and relationship, stability of the traveling wave with bifurcation problems have developed. So there are many applications. For example, singular perturbation problem and the gluing bifurcation problem. So two types. So two stable front and back glued. The pulse is stable or unstable. Also two unstable front and back glued the pulse. So pulse is stable or unstable. So there are many applications. Okay. So based on this idea, so here, so we introduce some example of determining the stability and in particular the instability of periodic traveling waves for some equation. This is collaborated by Miyaji now Kyoto University and Toshiyuki Ogawa, Meiji University, and also this is result of collaboration. So also we consider the equation 8. So equation 8 is the optimal velocity model. So one of our optimal velocity model. So in the numerical simulations, so we can show the equation 8 has a stable wave terrain. So in the numerical simulation, so right pictures. So parameter changes. So we can we change the parameter epsilon and alpha. So equation 8 has a parameter epsilon and alpha. So wave terrain is unstable, and so we can show that modulational waves, so spatial temporal periodic traveling waves exist in the numerical simulations. So we want to show that such waves why this solutions occurs, and so okay, so we consider spectral stability. Spectral stability of periodic waves. So we consider the stability problem of such waves. Okay, so with existence of traveling waves for moving frame, or in this is xi equals x plus ct. So it is equivalent to the equation 9. So like this, it is existence problem of traveling waves. So we can rewritten as the first order ordinary differential equation like this. Equation 10 is existence problem of traveling waves corresponding to vector field or four-dimensional Euclidean space. So simply expressed as like this. So this vector field depends on the parameter of c, speed c, and so alpha. So we fix the small parameter, epsilon is very, very sufficiently small. So we fixed because so existence, we use, so for the existence problem of traveling waves, we use a singular perturbation theory. So traveling waves exist for the sufficiently small parameter epsilon. Okay, next. So theorem 1. So there exists a family of periodic traveling waves with the following properties. So the wave train has a period L. And moreover, so two traveling front exist. So U plus and U minus exist. So for a specific speed C tilde. And so these solutions satisfy the following equation. So U plus traveling front then converge to the U0 and minus U0 tend to Xi to plus and minus infinity. And so U minus Xi traveling front U minus satisfies so this equation. So U minus Xi to minus U0 and plus U0 at Xi tend to plus and minus infinity. Okay, so theorem 1 means that so like this picture. So the family of wave train expresses as a family of periodic orbit for the first order systems, and traveling front are given by the heterogenic loop in the first order system. So like this, so theorem 1 means that such structure exists in the vector field for the specific parameters. So yellow lines means traveling front corresponding to the heterogenic orbit U plus Xi, and other one is other traveling front U corresponding to the heterogenic orbit U minus consists of U minus Xi, and for types, so U minus, V minus, and W minus, and Z minus. So U plus consists of small U plus, and
Yeah.
V. Okay. And so heterogenic group exists, and so inside of heterogenic groups, so there are many periodic orbit. Sorry. So red line and red UP Xi is a periodic orbit with a period L. So theorem 1, theorem 1 means that a period is in the minimum period to infinity. And so periodic orbit UP and the heterogenic group, it is a closure of a heterogenic orbit like this. So U plus and U minus, the closure of this set satisfies the following. So DH is a Hausdorff metric of a four-dimensional Euclidean space. So if we tend to the period, period L tend to infinity, so heterogenic orbit and heterogenic groups, so Hausdorff metrics over this set are equal to 0. So like this, so this picture means that this limit. Okay, so theorem 2. So theorem 2 is instability of periodic waves. So two traveling front are unstable, and the wave train is unstable if the period L is sufficiently large. So that is, there exists L star, such as periodic waves were unstable for all L larger than L star. And so corollary is given by as follows. So wave trains is destabilized by the Hopper bifurcation, and a spatial temporal periodic solution is generated if the period L increases so sufficiently large. So wave trains are unstable, and so Hopper bifurcations occur. Okay, so we consider the spectral stability problem. So similar as I introduced the stability index. So like this. So L star P equals lambda P. Where so star is plus and minus is also linearized operator for front, U plus and U minus. And star equals P is also linearized operator for, oh, sorry, it is a mistake. So linearized operator for the periodic waves. So UP. So we can rewrite as the first order ODEs, so like this. So equation 11. So rewritten as the first order ODEs, and so equation has so reversible symmetry over U component like this. So also A star has a reversible symmetry for U component. So it is also we remark that these have this symmetry, these symmetry. And so traveling front converges to the constant solution U0. It is depends on the parameter C tilde. C tilde is so speed, specific speed of wave front. And so U minus converges to the U0 minus plus U0. So this relation induced by the symmetry of U component. So this matrix, so A plus minus is so spectral problem with respect to the traveling front. So U plus and U minus. So these matrices tend converges to the constant matrix A0 lambda. So A0 lambda is so this also like this. So this matrix depends on the lambda and alpha. So we fix sufficiently small parameter epsilon, and so C tilde is fixed. So it is well known that the essential spectrum of linearized operator is given by this relation. So essential spectrum of A0 lambda is not hyperbolic for lambda. And so we can obtain this relation, so final equation. So this is also essential spectrum of traveling front, like this.
So do you mean some equality? So this is not relation. That's not equal. Do you mean something or?
So
What do you mean this?
okay, so this relation means that A0 lambda is not hyperbolic means so 4 eigenvalues in A0 lambda.
Yes.
And so at least one eigenvalues of
Should this relation to be zero, to be something equal to something or not? Okay, there's epsilon 1 minus alpha u naught squared, something like that. Is it equal to zero or something else?
oh sorry. So okay, I mistake. So it is lambda equal to this.
Okay.
Oh sorry.
Oh, I see.
Thank you. Very good.
Okay, I'm sorry, so I mistake it. Yes. Okay.
Mhm.
So yes, lambda is equal to this
Okay.
equation.
Very
Yes.
good.
Okay.
Thank you. Thank you.
Mhm.
Also, this curves like this.
Uh-huh.
Okay, so
Mhm.
so the essential spectrum of linearized operator with respect to traveling front is given by this curves, the red lines curve. So if epsilon is sufficiently small, so essential spectrum intersect the right side plane of a complex in the complex plane. So because of two traveling front U plus and U minus are unstable because of essential spectrum intersect right hand right side of a complex plane. So next, so we can obtain the unstable of traveling front. So next we consider the stability problem of periodic waves. So like this equation 12. So we considered these spectral problems in this functional space. So we considered bounded interval 0 to period L with periodic boundary condition. Because so if we consider the spectral problem of periodic waves on unbounded real line, so then all spectra of linearized operator consist of only essential spectrum. So we can use dynamical theory or topological theory. So we cannot use such theory. So, however, we consider the bounded domain 0 to L with a periodic boundary condition. So all spectra consist of only eigenvalues. Okay, so next we consider the first order systems with respect to periodic waves like this. So 13th, equation 13th. So this matrix has a period L because wave train has a period L. And so to express this, the periodic boundary conditions in linear subspaces, so consider the following extended systems. So consider the equation 14. So we suspend W dash equals 0. W is in 4-dimensional subspaces. Then we define the subspaces U par is equal to like this. So dimension of U par is equal to 4 because Y is in the C4. And so phi hat equal phi disjoint union and identity. So this is a fundamental solution matrix for extended systems 14. And where phi is a fundamental solution matrix for the also simple y dash equals AP, equation 13. Then lambda is an eigenvalue of LP if and only if such subspaces and U bar intersect non-triviality. And since the Hausdorff matrix converges to 0, periodic orbit and heterogenic groups converge to 0. So there exists L plus minus I, so I equal 1 and 2. So such relation holds. So AP nearly equals A0 for Cauchy is in L1 and L2. So this means that we can take Poincare section nearby the equilibrium U0 and minus U0. So we can take Poincare section, we have such L's. Okay, so we consider vector field is in the Cauchy in L1 and L2, L plus minus 1 and L plus minus 2. So we retrieve the information in such intersection problems through the following equations, so extended system. So the boundary condition expressed as a four-dimensional subspaces, so we can consider a vector field on the four Grassmannian manifold over four-dimensional subspaces, so G4, C8. We consider the vector field induces vector field on the G4, C8. So we remark that so boundary subspaces of periodic boundary condition, and so this subspaces is a point of the Grassmannian manifold. Okay, so define G is given by such a relation is in the Grassmannian manifold. So it satisfies the indices ordinary differential equation on the Grassmannian manifold equation 16. Then so lambda is an eigenvalue if and only if so this intersection is non-empty, so it has a intersection if and only if so lambda is an eigenvalue. So we consider such intersection problems is we consider the intersection problem in the Grassmannian manifold. Also, where so U per hat is also like this. This is also boundary condition of the Grassmannian manifold. Okay, so constant matrix as a lambda is so equal to like this. So and suspend system has so eigenvalues is so eight eigenvalues. One is also mu1 lambda is I omega lambda, and mu2 and mu3 and mu4, where so these real part of these eigenvalues are not equal to 0. And so 4 zeros because so trivial systems. So extended systems has a trivial systems, four-dimensional trivial systems. So and so okay, sorry. So lambda is in if so lambda is in essential spectrum. So A0 lambda is not hyperbolic. Not hyperbolic means that so at least one eigenvalue is equal to real part is equal to 0. So therefore, so we have the following properties. Okay, so in this setting, so we defined E1 is eigenspaces with respect to
So
mu1.
excuse me. So so in you can understand there are only one eigenvalue which is pure imaginary, right?
Yeah.
Mu1. So mu1 is pure imaginary.
mu1 is so only one eigenvalue of so real part of equal to 0.
I see. So this is a direct computation result.
Computation. So no. So it is so exactly so we can obtain so exact form of so eigenvalues of this eigenvalues.
Okay. Okay. I see.
Also, sorry. So it is so. I omit the so detail of so these hypotheses. So we take the hypothesis of so subset of essential spectrum. So we take so only one eigenvalue, which is so real part equal to 0. So like this.
I see.
And so other eigenvalues are not equal to 0. So such a real part is not equal to 0. So we can so we can obtain the exact form of these eigenvalues in this hypothesis.
Okay, I see. Thank you.
Sorry. So and so E1 is an eigenspaces with respect to such a only one eigenvalue of real part equal to 0. So it is invariant subspaces for phi hat, and so this equidistant system reduces E1 this and so disjoint union of C. So it means periodic boundary condition expressed as linear subspaces. So reduced system is given by the 17th. So this is a vector field on two-dimensional vector space, a complex vector space C2. And so it induces a vector field on CP1. It is complex projective spaces. Means that so CP1 is in the Grassmannian manifold, and so vector field expressed as this equation, so P dash equals the script P. Okay, so we consider the intersection problems is in CP1. So we can take two open sets, so N1 and N2 like this. So it is Y1 is not equal to 0, and so N2 is double tilde is not equal to 0. Of course, N1 cap to N2 equals to CP1. So in open set N1, we take Z1 equals this, like this. And so in N2, we take Z2 equals like this. So we obtain a concrete formula of a vector field P dash equals script P, so like this. And so in the open set N1, so in this coordinate, so induces vector field of one-dimensional complex projective spaces is given by like this, Z1 dash equals minus I omega lambda Z1, and the open set in N2, so Z2 dash equals I omega lambda Z2. So we can obtain vector field on the such coordinate. Okay, so it is immediately apparent that this solution produce a rotating flow on the two-dimensional sphere because CP1 homeomorphic to the two-dimensional spaces. So this equation generated the flow of which rotating flow on the two-dimensional sphere. So in particular, so it is also rotate monotonically with fan. So lambda is moved with in essential spectrum. So the parameter lambda moves in the essential spectrum. So also flow rotating in the two-dimensional sphere. So this means that the number of rotating rotating number means that it can evaluate the number of eigenvalues nearby the essential spectrum. So rotating number means a number of eigenvalues nearby the essential spectrum, and so in this situation, periodic orbit and heterogenic groups, the Hausdorff matrix converge to 0. So we have this relation, so L plus minus 2 minus L plus minus 1 to infinity if L tends to infinity. And so other one Okay, so yes, so this is so two relations. So it is so one is so vector field generates flow, which is so rotating flow on the two-dimensional sphere, and one is so this relation. So L2 minus L1 tend to converge to infinity. If so, the period L tend to infinity. So from this result or so relation, so it can be seen that when the period is increased, the eigenvalue of the wave train accumulates near the essential spectrum of the traveling front. So like this. So there are many eigenvalues of a wave train near the essential spectrum. So it means that the wave trains are unstable if the period L is sufficiently large. So this is a proof of outline of proof of theorem 2. Okay, so we emphasize that the analysis of flow of projective spaces, so Grassmannian manifold, used here is not a new technique. And so similar methods have been used in the stability analysis, also instability analysis of traveling pulses in the Fitz-Nagmo equation, showed by Chris Jones, 1984. So, okay, so we would like to apply the analysis of existence and stability problem, which has been performed on one-dimensional traveling waves to special multidimensional reaction diffusion systems and spatial temporal patterns. So we want to apply such problems. So outlines introduce. So stability index for multidimensional reaction diffusion systems are developed by Den and Ni, so, 26 and 28. So these are developed. And so recently, my research, Toshiyuki Ogawa in Meiji University, and so we tried such programs, three-component reaction diffusion systems has such a complex phenomenon. So it is so many wave trains. There are many wave trains, and so this pattern is a spatial temporal periodic patterns. So it is a modulated waves, and so there are many modulated waves exist in such patterns, and so this pattern is also given by the similar formulation like this. Modulated traveling waves is a solution of the first equation. So we can rewrite this equation like this and so like this. So first order ordinary differential systems. But however, this is a vector field on the infinite dimensional spaces because it has a derivative of time is in this system. So it is ordinary differential systems in the infinite dimensional spaces. However, such patterns obtained by this relation, heterogenic loops in the infinite dimensional phase spaces and homoclinic bifurcation occurs in such systems. Okay. Okay, so in this talk, so I omit the detail and so introduce a brief overview. So if you need more information, so please ask again anytime. That also, thank you for your kind attention. Thank you. That's all. Thank you.
So let's thank Dr. Sekisaka. Thank you for your nice talk. Do you have any question or comment?
Maybe not start. Okay. I have a very
Please.
general question. I am not very familiar with the stability of traveling wave, but I know some knowledge about Evans function, and this is an analytic approach. And why is your topological method better than the Evans function in your setting? Can I study the stability of the pulse or of your traveling wave by Evans function?
So your question is why I take
Yes.
a topological approach.
In your equation, for example, in your equation, you decide to use a topological approach, but not an Evans function, or maybe they are implicitly related. I cannot see it immediately. Yeah. Why the motivation?
One is my motivation is this relation is okay, yes. So it's classical problem, so Sturm-Liouville theory. Sturm-Liouville theory is means a number of eigenvalues means that zeros of eigenfunction. So it means that we can obtain topological invariant called as Maslov index. Maslov index is topological invariant for the Hamiltonian system. So motivation is
So, for example, can I calculate the Evans function and prove there exists a root of the Evans function in your setting? Is it easy or difficult?
So in general, construction of Evans function is so difficult.
Yes, I agree. Yes.
So, however, topological approach is not construct the Evans function, and other approach. So essentially, Evans function. Zero of Evans function is intersection of such subspaces. So eigenvalue problem is essentially intersection problem of such subspaces, and sometimes it is easy to show using topological approaches. However, always the construction of Evans function is very, very difficult because it is soluble of the vector quantum system. So
yeah, I want to make more comment. I know the construction of Evans function is very difficult, but if you have a spatial structure, like you have a singular perturbation, or you have a spatial topology on your vector field, then you can decompose your Evans function. Like there are so many Dutch guys, they do this research. But now I know nothing about the topological approach, but I am thinking, and you have to tell me whether it's correct or not. Is your topological approach is a kind of a decomposition of the Evans function? Is that true? Or they are irrelevant? Maybe Professor Zhang Juexin can help me because you know more about the Evans function. I know nothing. So.
No. I think Sekisaka-san, the key point is maybe a kind of index, right?
Yes.
The stability index, you can count the number of eigenvalue, right?
Yes.
So sorry. So in the topological approaches, so omit the detail of a eigenfunction. So for example, so norm of a eigenfunction or so very difficult to express. So
So, as I know, this work was first introduced by Alexander Gardner and Jones, right? They connected the Widen number, which is equal to the first chain number, right?
Yes.
Yeah.
Yeah. So such relations means twisting of a vector bundle. So it is unstable manifold of linear systems. So so for example, so in the bifurcation problems, so heteroclinic orbit and homoclinic orbit occurs in the, some bifurcation point. So it these structure depends on the also twisting of unstable manifold of such heteroclinic orbit. So Evans function can obtain such information. Of course, also the topological approaches obtain such information. However, approaches so different. However, two approaches is equal because Alexander Gardner Jones theory means that two informations are same information. However, for example, Evans function like Melnikov integrals or other one. So it is evaluated twisting and distance over to unstable and stable manifold. And so other one, topological approaches is twisting number is equal to the topological index. So for me, it is natural way to such topological approach is very natural way, and analytical approach is so hard.
Yes. Okay. I see. Thank you. Very nice.
Sorry, it very difficult to express my motivation. So my supervisor is Professor Yasumasa Nishura. So Professor Yasumasa Nishura always said why you use the topological approach, but I cannot express such motivation. But
Yeah.
this way is very natural for me.
Yeah. Yes, I totally agree that topological method should be easier or more applicable than analytic method. But it's a little bit weird that, so at least my friends, okay, most of them, they use analytic method. Nobody use the topological method. Can you explain why? Like, I don't know. Have you ever applied topological method to study stability? I never, but how can you explain this phenomenon? This is my curiosity. Maybe we can discuss afterwards. Okay, thank you.
Thank you.
So, any question?
Hello, can you hear me?
Yes.
Okay. So thank you for your nice talk. I have a small question about your slides, maybe the final slides.
Final.
You give a three-component system.
Yes, yes.
Okay, so do you consider traveling wave for this system, three component system?
Yeah. So we consider traveling waves
Okay,
for
so the traveling wave solution, the stability is already done or for traveling wave solution?
Existence problem is not done. So we assume is so traveling waves exist in such three component system. So however, so we can prove the stability of such waves.
Okay,
Yeah,
I see.
so existence problems is not done. So it is so difficult because so all however, so such wave trains occurs wave bifurcation. Wave bifurcation means so these three component systems in the two component system of U and V. So this system has a Turing pattern. So so special periodic patterns, and so added so W component. So this equation bifurcated and so Turing pattern unstable, and so wave trains occurs in this system. So I think so we can prove that so such wave train is so stable because this wave train occurs so Hopf bifurcation of a Turing pattern.
I see.
However, so it is not done.
I see. Thank you. Yeah, because it's three component system, so I'm curious. It should be really difficult to study stability.
Yeah, so difficult.
Okay. Thank you.
No, thank you.
So is there any other question or comment?
Let me ask another one. Can you go back to your this loop, like heterogenic chain and also this periodic solution inside the slides of that, any slides, like this loop and the periodic solution?
Oh, sorry. Oh,
I don't remember the page, but you have made a picture like two equilibrium and a
okay.
heterogenic
So,
chain. Yeah, and this one. Yes, like this one. And this picture, face portrait, remind me of the pendulum equation, right? Like the U double dot plus sign, you something like this. But now you have a four-dimensional problem, right? Your OD is four-dimensional.
yes.
And now you told me that these periodic solutions are inside the heterogenic chain. But now, because of four dimensionality, we don't have a Jordan curve, we don't have a Poincare Bendixson. How can you make sure that in the full four-dimensional space, your periodic orbit cannot go out, wind around? You know, there are so many weird possibilities. And have you proved this? Because I noticed that in your field, you just use a continuity to prove the stability, continuity of the Hausdorff distance between the periodic orbit and the heterogenic chain. But is this face portrait correct in the four-dimensional space? This is my question.
Okay. So, yeah. So your question is why in this system is in the four-dimensional spaces. However, so this picture.
No. I am asking now the picture you have. It's a projection of the four-dimensional to the two-dimensional plane.
Yeah.
Is this true?
Yes, true.
Okay.
So, okay. So your question is original equations. Okay. Yes. So, we prove that existence of traveling waves and periodic heterogenic orbit. So we use the singular perturbation theory. So this equation, so epsilon tends to 0.
Yes.
Yeah. So this system has three orders differential. Yes. And so integral over was. So we have so
I
this.
see. This is very special. When epsilon is 0, this is almost the pendulum equation. Okay.
Yes. So this system has a abelian integrals. So this convert conservation laws. So
I see.
yes.
I see.
So
Very
we
nice.
constructed two-dimensional cases. So we assume that epsilon is very sufficiently small. Yes. So
very nice. Thank you.
like this picture, nearby the two-dimensional subspaces.
Thank you.
Sorry, thank you.
Yes. So this is in your leading order term. This is KTV equation, right? It is.
Sorry. So one more, please.
So the equation 9, the leading term is KTV equation, right?
Yes. So this equation is called as a modified KDB equations.
I see. Modified KTV equation with perturbation term to fourth order, right?
Yeah. So yeah. Sorry.
Yeah. Perturbation term is to fourth order. Yeah.
Yes. So perturbation term is fourth order. Using singular perturbation theory, usual singular perturbation theory cannot apply because higher order term is in the perturbation term. However, this system has abelian integrals, conservation laws over. This system has also pen epsilon to 0. So this system has sorry. Sorry. So I forget. Sorry.
So in your proof, in your page 31 maybe.
31.
Yes.
Pages. Sorry. So I can 31.
31. Yes. 31. Previous page. Yeah, this one. Yes. So could you explain why you want to with the additional equation W prime equal to 0?
Yeah.
So I don't know what's the purpose with the additional equation.
Yes, so it is because first we want to express it as boundary conditions to the linear subspaces. So like this, your part is a periodic boundary condition. So if we do not consider extended systems, so periodic boundary conditions cannot express it as a linear subspace. However, it is equivalent to the Floquet matrix. So we can take a Floquet matrix. So if we take a Floquet matrices theory, Floquet theory, so this extended system is not needed. However, I want the eigenvalue problems lead as intersection problems to subspaces. So we can express it as a periodic boundary condition to the linear subspace like this. So to this expresses, so we extend to this system extend to the trivial equation. So, your question is means that why is so lambda is eigenvalue of so if and only if this intersection is not trivial.
So I also don't understand. So phi hat is a fundamental matrix for equation 14, right?
Yes, yeah,
Yeah.
yes.
But U per is 4-dimension, right?
Yes, 4 pi is a 4-dimensional subspace. Yeah.
Maybe can I make a remark about Professor Zhang's question? So in the original equation, nonlinear, you have to find a periodic solution and also the period. There are 4 periods because you have a four component. So the periodic wave and also the period are unknown. Now you incorporate the unknown 4 real numbers into the extended system, and then you linearize. Then you obtain this y product and w product equation, I think. So already from the very beginning, you increase you consider extended system, I think. So this is my guess.
So what do you what do you mean, for Professor Dai? So
okay, so you want to find periodic solution. This is like traveling wave problem. Traveling wave and the wave speed, they are unknowns, right? Then for periodic solution, the periodic solution profile and also periods are unknowns, right? Now you consider extended system. This W prime incorporated the period. They are real numbers, so W prime is 0. And then after you find the existence, you solve the existence problem, you consider linearization. And because W prime is 0, the linearized system is the same. Then you consider this extended linearized system. Yeah. This is my
so maybe the W component as period, right?
yes. I think they play a role as period.
Oh, because it's always a constant, so W prime is always 0.
Yeah. And they are 4 period because of 4 because there are 4 components. I think maybe I am not quite sure, but I guess. Yeah.
So Sekisaka-san, is our discussion true or not?
All nonsense.
So difficult
Do you understand?
So
Maybe we can ask, do we have to consider extended system to study the stability?
stability?
Yes. Is W prime is equal to 0 very important or not?
Yes, this extent is important because so periodic boundary conditions realize so linear subspaces so like so U pi is so periodic boundary condition of the left hand side and the right hand side. So W prime equal to 0 induces fundamental solution matrix is identity because so initial data to initial data. So so the W prime equal to 0 has a fundamental solution matrix over identity. So okay, so if so periodic solution is in the yes, 13. So y dash equals APY has a periodic solution. Then, so the fundamental solution matrix phi is a fundamental solution matrix of so 13. So phi has a sorry. So we so phi L0 lambda. So we consider the phi L0 lambda. It is a Flock matrix of this system. So phi L0 lambda has one eigenvalue if and only if so system 13 has a periodic solution. So it is so Flock theory. Yeah. So so another realized such information so is given by the extended system, and we consider the extended systems, and so boundary conditions realize so linear subspace. So we
take a look on your boundary condition. Can I take a look on your boundary condition, periodic boundary condition? Why is that?
Sorry, one more please.
What is your periodic boundary condition? Can I look at it? Take a look. Where is the periodic boundary condition?
Oh, sorry, I don't know so your question. So
is the 13 equation 13 the boundary condition? The second one, right?
So equation 13.
Yes.
Okay. So so yeah, boundary condition. So we want to show the periodic solution in 13. So 13, so equation 13 has no boundary condition. So we consider this equation on the interval 0 to L. So
okay. Because I am thinking, why you introduce 4-dimensional space W for the period, but not just one? Are you considering quasi-periodic solution? I am a little bit confused, but yeah. But I'm still thinking. Yeah. Okay.
Also, sorry. So, for example, so direct boundary conditions means so realizes that linear subspaces in the 13. For example, so this is so okay.
Yeah.
So yeah, sure. So U dash equals V, V dash equals W. So direct boundary condition is so U equals 0. And so Neumann boundary condition. So if we consider the reaction diffusion systems, so we consider Neumann boundary conditions realize that so V dash equals 0. Sorry, so V equals 0 because so V equals U dash. So Neumann boundary condition means that so U dash equals 0.
Yes.
So each so Dirichlet and Neumann also Laban type homogeneous Laban type boundary condition realizes to the linear subspaces in the first order system.
Yeah.
However, so periodic boundary condition is not expressed as a linear subspaces in 13.
Yeah, I see. Thank you.
Yeah, so we want to realize the linear subspaces in the boundary condition. So periodic boundary condition we extend that W prime equals 0. So in this extended system, so periodic boundary condition realizes so linear subspaces such as U path, so 4-dimensional subspaces.
Okay.
Thank you.
Oh, sorry. So thank you.
Okay. So, is there any other question or comment?